How does the temperature of a gas affect the gas's pressure? Let's look at some ideal data to help us to see patterns and to answer this question. Here, temperature has been increased, the resulting pressure has been measured, and there are some missing values that you need to fill in. Look for patterns in the data to help you to fill in the missing values. So let's compare the temperature and the pressure for lines 1 and lines 2. We've increased the temperature 1,07 times. 293 times 1,07 equals 313. As a result, the pressure has also increased by that same factor. Obviously, 1 times 1,07 equals 1,07. Let's take lines 2 and lines 4. It really doesn't matter which lines we take. 313 times 1,13 equals 353, and 1,07 times 1,13 equals 1,21. We've increased the temperature by a factor and the pressure has increased by that same factor. In other words, temperature and pressure are directly proportional to one another. So now we need to solve for our unknown values. First of all, of course, we need to convert this temperature in degrees Celsius into Kelvin. We add 273 and we get our answer. Now we need a comparison state to compare with this question state. So it really doesn't matter which one we take. Let's take line 4. So by how much have we increased the temperature? That's the same factor by which the pressure will increase. And that factor is 1,06. We find that by 373 divided by 353. And so we can find our answer by multiplying 1,21 by that same factor. And the answer is 1,28. Let's use that reference line again, line 4, to solve for the unknown pressure in line 6. We find the factor by which temperature has been increased, that's the same factor by which pressure is increased, and that gives us our answer. Then to solve for the last unknown, we must minus 273 from the Kelvin temperature to find the degrees Celsius temperature. Now let's solve for these unknowns again using another pattern. In fact, it's the same pattern, but just put in another way. Notice that in this data, whenever you divide the pressure value by its associated temperature value in Kelvin, you get a constant. In this case, the constant is 0,0034. And so that must also be the case for the unknown lines of data. So you can use algebra to solve for that. Let's formalize that in an equation. Let's call line 1's temperature T1 and its associated pressure P1. So we can see that P1 divided by T1 is equal to a certain value, a constant. And the same applies for the second line of data. Let's call its values T2 and P2. And P2 divided by T2 equals that same constant that P1 divided by T1 equaled. And so P1 divided by T1 equals P2 divided by T2. So let's use this equation to solve for an unknown value. Let's put the question in words. An enclosed mass of gas has a pressure of 1,21 kilopascals when its temperature is 353 Kelvin. What would its pressure be at a temperature of 373 Kelvin? Here we have that same question, but in the table and with the unknown value as a question mark. Notice we have a question state and a comparison state. Let's call the values in our comparison state T1 and P1, and in our question state T2 and P2. We substitute into this equation and we need to solve for P2. We cross multiply and then divide both sides by 353 to find P2, 1,28 kilopascals. We know that the unit is kilopascals because that was the unit of pressure 1. So notice that we found the same answer using the equation as we found when we used proportion, and that's because the equation is using proportion. So let's answer this question. How does the temperature of a gas affect its pressure? We've seen that the pressure of a gas is directly proportional to its temperature in Kelvin. This is only true, though, if the other variables, volume and amount of gas, are controlled. But by us stating this, we are implying that those other variables are controlled. Let's put this statement into an equation. Pressure is directly proportional to temperature.